9th standard ICSE chemistry chapter 7 from Anita Prasad textbook, study of gas laws. The introduction is entirely marked as read, not very important. It's a history of how these cool dudes with cool hairstyles discovered some laws like Boyle's law, Charles' law, Avogadro's law, etc. That's what we're going to study in this chapter. Well, Boyle's law and Charles' law, Avogadro's law is in 10th standard. These laws explain how pressure, temperature, volume and the number of particles in a container of a gas are related. Laws for gas are special because these laws are applicable only for the gaseous state of matter, not for liquids and solids. You see, gases are unique. Their intermolecular space is so much that the actual size of the molecules is negligible compared to the total volume. Now there are three definitions here. Pressure, it is a ratio of the force of the gas exerted on the walls of the container per unit area of the container. We know that pressure is force upon area. So here the pressure is exerted by the gas on the container. In fact, if the gas is in a balloon, the balloon inflates, it expands because of the pressure of the gas. Temperature is always the measure of the average kinetic energy of the molecules of a substance. Its SI unit is Kelvin. Volume is the space occupied by the gas. Unlike solids and liquids, gases don't have a fixed volume. They don't have a fixed shape. Let's study some properties of gases. How is it different from liquids and solids? Solids have a definite shape and volume and they cannot be compressed. They are rigid. Mark the definition. Here also liquid definition. They have a fixed volume but no definite shape. They take up the shape of the container and they are also called fluids because they flow and they can be compressed to an extent. Gases have neither volume nor shape. They take up the volume and shape of the container. It is also a fluid. It also flows. It is highly compressible. Why are solids rigid and why do they have a fixed volume? Because of the strong intermolecular attraction and the low intermolecular space. Mark it as a given reason. Liquids have intermolecular attraction but it's less compared to solids, and the intermolecular space is more compared to solids. That is why they can be compressed to some extent. Gases hardly have any intermolecular attraction left, and the intermolecular space is maximum compared to the other states. So mark this as a good reason as well. There's a fourth state of matter called the plasma state, and then the fifth state is the Bose-Einstein condensate, but all that is not in school syllabus. Now we have a few given reasons. Why do gases not have a definite shape or volume? Why are they highly compressible? Why do they exert pressure in all directions? It's mostly because of the random motion and the high kinetic energy of the molecules, the weak intermolecular force of attraction and the large intermolecular distance. That explains all its properties. Why do they have low densities and why do they diffuse so easily? If there is an LPG leak, you can smell it immediately far away. Why do gases flow so fast? And why can they be liquefied very easily under high pressure? That's because when you apply pressure, volume decreases. The molecules come close to each other, and when they come very close to each other, they become liquids. And that is Boyle's law. If the temperature is constant, then the volume of a given mass of dry gas is inversely proportional to its pressure. So as the pressure increases, volume decreases because as there is more pressure, the molecules come closer to each other, the intermolecular space decreases, which means the intermolecular attraction will also increase and the volume will decrease. So if I were to draw a graph, it would be like this. Mark this couple of points as read. Stable is also just read. These graphs, tick them and learn them. If it's V versus 1 upon P graph, it's a straight line because we can say that volume is directly proportional to the reciprocal of pressure. But volume is actually inversely proportional to pressure, so it's a curved line. And PV versus P graph is a flat line, horizontal line. Now this is another way of writing the Boyle's law, learn that by heart. The equation we will use for numericals is P1V1 is equal to P2V2. Learn all these conversions, how to convert one unit into another. It will be useful during numericals. Boyle's law can be explained with the help of kinetic molecular theory. As I explained, gases have molecules which have high kinetic energy, moving in a zigzag manner, random motion. But as the pressure increases, the volume decreases, because now we are bringing the molecules close to each other. Note that temperature is constant, means the average kinetic energy is constant. Now the reverse is also true. If I halve the volume, the pressure will double. Notice how here the pressure is 1 and now the pressure is 2. You see, pressure is dependent on the frequency of the collisions of the gas molecules on the walls of the container. If the volume is halved, the number of collisions per second will double. So the pressure will also double. So they are inversely proportional. Boyle's law in daily life. Well, it helps us in breathing. You'll study this in Bio chapter 14, respiration in animals. So when the diaphragm muscle contracts, it goes down, increasing the thoracic cavity, the chest space volume. And as the volume increases, the pressure decreases, and air always flows from higher pressure to lower pressure, and that's how we inhale. And that's why the lungs expand. We don't inhale because the lungs expand. The lungs expand because we inhale. And in exhalation, the opposite happens. The diaphragm relaxes, its dome-shaped curvature is obtained again, and the rib also goes inward. So the chest volume decreases, pressure increases, and the air is exhaled out of the body. Scuba diving. Mark this as a good reason. It's very important that as the diver comes to the surface, he should do it slowly. Because if he has got used to a great depth where the pressure is much, and now suddenly if he comes to the surface where the pressure is less, then when the diver ascends to the surface, the pressure is decreased, which causes the volume of the air in the body cavities to expand, which can be risky for his life. His organs may just burst. The air in his blood may form large bubbles, create obstructions. Charles' law. Charles' law says that as temperature increases, volume increases, assuming that the pressure is constant. And that makes sense as well as per the kinetic molecular theory. As temperature increases, the kinetic energy will increase. So the number of collisions with the walls of the container will increase. But if I want the pressure to remain constant, if I want the frequency of the collisions to remain the same, I will have to increase the volume. So as far as pressure is constant, as temperature increases, volume increases, directly proportional. So at constant pressure, the volume of a given mass of the gas increases or decreases by 1 upon 273 of its original volume at 0 degrees Celsius for each degree Celsius rise or fall in temperature. This is quite a complex language. So instead of using degree Celsius, if we use Kelvin, then the law becomes very easy, which is pressure remaining constant, the volume of a given mass of a dry gas is directly proportional to the absolute temperature, meaning Kelvin temperature. So Lusac modified Charles' law and made it easy. And a new scale of temperature was invented, the Kelvin scale. In the Celsius scale, melting point of ice is 0 degrees Celsius and boiling point is 100 degrees Celsius, which is divided into 100 divisions. In the Kelvin scale, we took the melting point of ice as 273 and the boiling point of water as 373, and even here divided them into 100 divisions. So 1 degree rise in centigrade temperature is equivalent to one unit rise in Kelvin scale temperature. No degrees for Kelvin. Lord Kelvin had degrees from his college, but while writing Kelvin, we don't mention degree sign. Only for Celsius and Fahrenheit we do that. Now the lowest possible temperature in the universe is minus 273 degrees Celsius, which is taken as 0 Kelvin. Nothing in the world has ever reached this temperature and cannot reach this temperature, because as temperature decreases, volume decreases. So mathematically, at 0 Kelvin, the volume will become 0. But how can an object just disappear? That's not possible. Hence, we have not reached this temperature. We have reached a millionth of a Kelvin above the temperature in the lab settings using lasers and science and technology. But 0 Kelvin is not possible. It's called absolute zero, the lowest temperature theoretically possible. And practically also, we can't reach this temperature because before that, the gas would have become a liquid. But even the liquid or the solid cannot reach 0 Kelvin, by the way. Absolute zero, mark it as a definition. Absolute scale also, mark it as a definition. Know how to convert Kelvin into degree Celsius and vice versa by subtracting or adding 273 respectively. This paragraph is just read. Graphical representation, well, mark it as read. It's a solved example that you'll do when you do numericals. Right here, solve. That's not for the homework right now. They are directly proportional, so obviously the graph will be a straight line. If we would have used degrees Celsius, then the graph would have looked like this. But if you use Kelvin, then the graph starts from the origin of the graph paper. Kinetic molecular theory, I've explained how that works. There are some assumptions here. 2 assumptions, so learn them. 3 assumptions. First is that the volume of the molecules is negligible compared to the total volume of the gas because molecules are so small. Second is that gas molecules, they are in random zigzag motion and they collide with each other in a straight lines. And third is that the collisions are elastic, meaning the momentum and the energy is conserved. So the average kinetic energy of the molecules is directly proportional to absolute temperature, meaning Kelvin temperature. How is this applicable in daily life? The working of hot air balloon. When you heat the air, the volume increases. If the volume increases, the density decreases. And if the density decreases, then it starts floating. Instructions on a deodorant bottle warns that it should be kept away from sunlight because high temperature will cause the molecules to increase their kinetic energy. The bottle will expand and it could burst the bottle. That's why the tire tubes also burst during summer season. So give reason here. Basketball also increases in size in summer. Give reason here. Give reason here. The rising of bread and other baked goods in the oven are caused due to the yeast, which releases carbon dioxide gas. And when the oven heats up, the carbon dioxide gas expands, causing the dough to inflate and leaving pores in the baked goods, making them light, soft, spongy, porous. The gas equation. Well, if you combine Boyle's law and Charles' law, and you get a single equation, P1 V1 upon T1 is P2 V2 upon T2. Otherwise, Charles' law was simply V1 upon T1 is equal to V2 upon T2. But here we are assuming that pressure is constant. And Boyle's law, we assume that temperature is constant. What if nothing is constant? And in real life, one term cannot be constant during any change. So that's when we use this gas equation. There's a give reason here. Why do we use a standard temperature and pressure? Standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atm, that is a sea level air pressure. Whenever you want to compare two gases, it's better if their temperatures and pressures are equal because gases are very sensitive to the slightest change in temperature or pressure. Their volume changes quickly, unlike liquids and solids. So it's better to compare gases at the same temperature and pressure. And a standard has been chosen by scientists, which is called SPP. So now this is a good reason. Again, it's a numerical to be solved whenever you get a homework in the future. Effect of moisture on pressure is marked as read. But if your teacher wants you to learn this, then just learn the definition of partial pressure. So if the gas is dry, well and good, but sometimes there is moisture in the gas. So the actual pressure of the gas will be the initial pressure of the gas plus the pressure of the water vapor. No numericals based on this will be asked. Chapter review has to be solved. Page 166 has solved examples, even page 167 has solved examples. You have to practice them whenever you are given homework. Then we have the exercise. Theory questions, you just have to mark the answers. Numericals have to be solved. Self-evaluation test also needs to be solved whenever you get that homework.
Hi students, this is AJ sir. If you found this video useful, press the like button. Also, if you'd like to enroll for my test series or online lectures, email me or message me on Instagram. Check my description for more information.